بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Let's get started with a new lecture on our course Deep Learning and Convolutional Neural Network. And today we are going to learn about deeper neural network. So this is a small reminder about the last lecture where we have a neural network, a basic neural network with one hidden layer and one output layer. And this is the summary of the forward propagation that we have achieved. Okay, so assuming here that you have an input image and you have a first hidden layer which is A1 and a second hidden layer that is A2, and here we are going to provide a batch of M images into the input of the neural network to finally calculate the whether the image contains a cut or doesn't contain a cut. So the output will be just one of two possible values, either 0 or 1. So we calculate here a certain probability y, and then if it is greater than 0.5 it will be equal to 1, or smaller than 0.5 it will be equal to 0. So it will make binary classification. And we have established the different equations for the forward propagation. Here we have calculated the output Z1 in the first layer equal W1 X plus B, and X here is the matrix of the M training images, plus B1 which is the bias, and then we calculate A1 by applying a nonlinear function J to Z, and G here we have seen that it can be sigmoid or ReLU or tan H or any of the nonlinear activation functions that we have introduced in the previous lecture. And after calculating the output A1 of the first hidden layer, we're going to use it as input for the second for the output layer A2. So here Z2 we will calculate it as W2, which is the weight in this layer, multiplied by A1, and A1 here is the output. So maybe I have a small mistake I need to fix, is that here is A is capital. Okay, and A capital, it means that we are training M training examples, and if I put A small, it means for one training example. Okay, since here we have M training example, we multiply W by A plus B2, which is the bias in the output layer, and finally we apply nonlinear function and we calculate here A2 equals Z sigma 2. Of course, we have also introduced the shape of the different matrices. So we start by X, which has n X pixels, okay, which is the number of rows here, and it has M training images, which is the number of columns. And this makes that W will have nx values to be able to make the dot product, okay, nx columns, and it will have nl1 rows. What is nl1 here? L1 is the number of nodes in the first hidden layer. Yes, in layer 1. Okay, and now making the dot product, we will have nl1 by m, and here we have nl1 by m, which is the shape of okay, so it's not by m. I have another error because b doesn't depend on m. So we have nl1 by 1, and we do broadcasting to calculate z1, which is nl1 by m. So here z1 depends on the training example as we have introduced last time. And here we calculate a1 equal to z1, so it will be have the same shape, and then the shape of a1 will be nl1m, and the shape of w2 will be 1 nl1. Why we have 1 here? Because we have one node in the output layer. We have one node, so usually here what we put is the number of node in the layer L2. And using the same thing, so we're going to have the shape of Z2 as 1m. And finally, we calculate the shape of A2, which will be 1m and 1m. This is the correct formula. Okay, so we
Doctor,
yes,
if we have more than two classes in the prediction, we can't use sigmoid, right?
we cannot use if we have two classes in the prediction. Yeah, in the output layer, we don't use sigmoid, we use
Yeah.
the softmax. We use the softmax function, like we did in the TensorFlow example.
Yeah.
Yeah. And of course, at the end of the forward propagation, you need to calculate the cost function, which depends on W1, B1, W2, B2, which is just the average of all the losses from M training examples. So in the same way, we have calculated the backward propagation. Okay, of course, this backward propagation considers that we have a cross entropy loss function, which is the log loss, and it will give the following derivatives that we can calculate in the backward direction. We calculate dz, dw2, db2, and then dw1 and db1, and the resulting values will be used to adjust the values of W1, W2, B1 and B2 in the same way that we have seen in the basic example of logistic regression. Okay, so yeah, this is the case, the difference between case of one training image and the vectorized backward propagation. And in the implementation, in the execution, we usually use the vectorized version because it is much faster and optimized computation. Okay, so this was the summary of the forward propagation rules and the backward propagation rules when we have a neural network with one hidden layer and one output layer. So today we would like to generalize these equations for a deeper neural network. What does it mean, deeper neural network? It means it has multiple hidden layers. Okay, for example, like you can see here, we can have one input layer and one output layer and three hidden layers. So this network is deeper. And of course, as you add more hidden layers, your network is going to become deeper and deeper. And usually we need to add more hidden layers if the input data is complex and we requires more nodes and a deeper network for extracting the features and for the classification of the data. So the learning outcomes for today's lecture is first to see deep neural network as successive blocks put one after each other. Okay, so you can see that a deeper neural network is nothing but just the generalization of the equations that we did it with one hidden layer. Instead of having one hidden layer, we're going just to have stacked number of or stacked blocks of neural network layers. And then you will also build and train a deep L layer neural network, and you will analyze the matrix and vector dimensions to check neural network implementations. So today we are going also to talk about the shape of the weight matrix, the bias, the output Z and A when we have deep neural network. And this will help you later on in the assignment to care about the shape when you do the implementation. You will also understand how to use the cache to pass information from forward propagation to backward propagation. And these things you will do it in the assignment, because now in the previous assignments what you have done, you had only one layer, so you not really to have it was simple to calculate the backward propagation. But here, when you have multiple layers, the backward propagation is going to a little bit more complicated, because you need to keep the information of the previous layers when you calculate the derivative in the backward direction. So this is going to be more clarified when you make the new assignment. And understand the role of hyperparameters in deep learning. So let's first analyze different types of neural network architectures. So here the basic, or what we call logistic regression, is the basic neural network with only one neuron, and you have input data here to this neuron, and finally you calculate one estimated value between 0 and 1. This is what we call a shallow network. Shallow because we don't have we don't have hidden layers. We have only one layer that is at the same time hidden. It is just an output layer. We don't have even any hidden layer here. And in the previous lecture, we did an example with 2 layers. And 2 layers here, we have one hidden layer. And you can observe that we don't count the input layer. When we say that we have a 2-layer neural network, it means that it has one hidden layer and one output layer. Okay, so this neural network is only 2 layers. We don't see that we have 3 layers. The input layer, we don't count it. And this is now a bit deeper network with 3 layers. Okay, so 3 layers, it has 2 hidden layers. So the first hidden layer, it has 4 nodes. And the second hidden layer, it has 3 nodes. And finally, it has an output layer with only 1 node. And this is an example of 4 hidden layers, and it's called a deeper 5-layer neural network. We have 4 hidden layers and 1 output layer at the end. Okay, and of course, we can go deeper and deeper, and even the number of layers is one of the hyperparameters that you can change to check what is the impact on the classification problem.
Doctor?
Yes.
Yeah, I've seen usually that when you go through layers 1, 2, 3, they always have the same nodes or decrease.
No.
I don't think I've seen something that decreases and then nodes, then the other layer goes up, the one after it. Is it possible?
Yeah, it's possible. I mean, if later on when we do encoder decoder, you can see that, okay, if you do encoding, when you go deeper, you are going to reduce the number of nodes in every layer. And when you do decoding, you will do the opposite thing. Okay, but in the architecture of classifiers, usually we go from more nodes to smaller number of nodes. Why? Because in every layer, we try to reduce the number of features, okay, to be able to do the classification at the end. Because
sorry again?
In every layer, we try, when we go from one layer L to L plus 1, we try to reduce the number of features. Okay? You can see it as dimensionality reduction. This is the objective. So this is why we try every time we are going to reduce the number of nodes. But nothing prevents you to do, like sometimes you increase or decrease. But I'm not sure whether this is going to lead to something good. I mean, now the common way to implement that is from the first layer have larger number of nodes than the last layer at the tail. Okay?
Okay.
Okay. So let's now look again at the neural network notation. It's basically the same notation, but here we will do some generalization. So here observe that we have layer 0 to layer 5. Okay, layer 0 is just index 0 because it's not even counted. And we have the first hidden layer, the second hidden layer, the third, the fourth hidden layers, and finally layer 5 is the output layer. So NL, L between brackets, okay, it's the number of units in each layer. So if we apply this, we can write that N1 is equal to 4, because here we have 4 units or 4 nodes. N2 is also equal to 4. Okay, N3 is equal to 4. N4 is equal to 3 because we have 3 units, and N5 is equal to 1. So this notation, it means the number of units in the layer L. And okay, so we can also calculate the activation function at every layer. So AL will be all the activations of this layer, the first layer, from one training example. Okay, and AL is nothing but GL multiplied by Z. So here, if we use Z like this, Okay, if we use one training example, maybe it's lowercase to be consistent. Okay.
Doctor,
Yes.
the neurons, the lower number, it should be like in the first layer 1, 2, 3, 4, because it's 1, 2, 1, 1.
Which layer? Can you tell?
And all of them, the lower number, isn't it the number, the node number or the neuron number?
The ID of the node. Yes. So this is A11. It means the output in the first node of the first layer.
Yeah, because the two in the bottom, they're 1, 1 also in every layer.
Yeah. Sometimes the copy paste, I have to change it, but of course this should be 1, 2, 3, and 4.
3, 4.
Yeah, maybe you can just fix it.
Doctor.
Yes.
We made Z small because it's one training example, right? Same as we did with A.
Yeah. For the consistency, we use A and Z capital when we have M training examples. Okay, yeah, so this is the notation. It's basically similar to what we have done in the previous time. So now our objective is to calculate the forward propagation in every layer and also the backward propagation, okay, for the same thing. Okay, so let's start by the forward propagation. So we will do in the same way. We are going to calculate the Z value at every layer. So you can find Z1 is W1 multiplied by X, and here I use capital. Okay, I need to make some cleaning on my code, unfortunately. Okay, small glitches. Let me just fix them now. I will try to upload you the new slides, at least you have the notation consistent with what we have introduced.
There's a small A in the middle.
Yeah. All this A has to be changed. Sometimes it becomes confusing, a lot of notation. Okay, I think it's done. Okay, so as I mentioned here, we have to calculate Z1, which is W1X, and X contains M training example plus B1. We calculate A1. So A1 will be the input for the second hidden layer, and you are going to calculate Z2. So it's basically the same thing that you have done. The only difference is that layer 2 now it's a hidden layer instead of being an output layer. You do the same thing with A3 to calculate Z3 and A3, Z4 and A4, Z5 and A5, and here A5 is the output layer. And finally, from A5 we calculate the Y hat, which is the output at the layer L, and L capital, it means the number of layers that we have here. We have L equal to 5. So this is the general equation for the forward propagation with 5 layers. So now we can write the following. Okay, and again. So now we can have the general expression of the layer L for one training example, or for M training example. I think I confused a lot here. Because of the notation. It's ZL, WL, AL minus 1 plus B, and AL equal GL by ZL. Okay, so look here. Here we use L minus 1 because the output of L minus 1 will be the input for the layer L. Is it clear?
Yes, doctor.
Okay, yes, and this is the vectorized version for Okay, so this is the vector for M training examples. Yes.
Doctor, G, that's mean activation function, right?
G? Yes. So G, it's an activation function, as I already mentioned in the beginning. It can be sigmoid, it can be ReLU, it can be 10H. So basically here the output layer is going to be sigmoid because we have an output either 0 or 1. But all in these layers, it can be any of the activation functions, ReLU or 10H or any other, or sigmoid or any other. Okay. So this expression is the vectorized version for M training example. And of course, A, you can see A, it's the same expression. Okay, here we have the output at every unit or every node. And here we have for M training example. So here we have the number of training examples. And here we have the number of units in the layer. So for the matrix dimension, we can check the case of one training example, how to calculate it. Okay, basically it's the same way. So now considering this network, we have 3 hidden layers, 3 hidden nodes, here 5, here 4, here 2, and finally 1. So X, what is the shape of X is 2, 1. So W is going to be 3, 2, because here we have 3 hidden nodes, and B will be 3, 1. So this results in Z being 3, 1, and of course Z is going to be this output. And you calculate A1 of Z by applying a nonlinear function, so it will keep the same shape. And we do the same thing in the second layer, in the second hidden layer. So the input will be just A1 from one training example, and Z2 will be equal to W2, and the shape of W2 will be 5, 3, because here we have 5 nodes, and here we have 3 input elements. Multiplied by B2 is equal to 5, 1 plus B2, and we calculate A2. So we can write that the general equation, okay, the general shape will be the following. Okay, so for at every layer L, the weight, the shape of WL is NL minus 1. So NL minus 1 represents the number of units in the previous layer, and NL represents the number of units in the current layer. And then the shape of A will be NL minus 1, 1. And the shape of B will be NL 1. We have one bias in every node of the layer L. And then we calculate yes, just one moment. We calculate NL, we calculate Z, so it will have the shape NL1. And finally, the shape of A will be the same as the shape of Z. Yes, Talal.
Units, do they mean neurons?
Yes,
like
nodes.
nodes?
Yeah, we can say neurons or nodes or units. They all mean the same thing.
Okay, I have 2 questions.
Yes.
If you go back to the previous slide, the last one of the previous section. Yeah, so it says the number of columns corresponds to the number of training examples, but actually it corresponds to the number of layers, because it ends at M. Isn't that correct?
No, M is the number of training examples. And here, for example, if we take layer 1, it has 4 nodes, 1, 2, 3, 4. So 1, 2, 3, 4. This is the number of units or the number of nodes. And here is the number of training examples.
Sorry, I got confused.
First training example, second training example, nth training example. It's the same thing that we have seen even in the previous lecture.
Yeah, and I have one question. If you go to the next, the first slide, the next section.
This?
Yes. So we made the W in the second layer 5 by 3. So I get the 5. It's the number of units.
Yes.
But why did we make it 3 in the previous layer, which was 2? Because it's a.
Okay. Why W2 is 5, 3?
Why the number of columns is 3, and in the previous one the number of columns was 2.
Okay. Who has the answer?
The previous one was 3.
Yes, because the number of nodes in the previous layer is 3. And this is why here we made the general rule. It's NL minus 1. So NL is equal to 5. NL minus 1 is equal to 3.
Okay.
And this number should have the same number as the output of layer 1, which is 3, because you have 3
the number
outputs.
The number of columns in a layer corresponds to the number of rows in the previous layer.
Yes. واضح شباب؟
Doctor,
Yes.
when you say the number of training examples, you mean the number of images in the dataset?
The number of images in the dataset. Yes, the number of images in the dataset.
Doctor,
Yes.
this formula is for n bigger than 1, right?
Yes, it's a general formula. It can be applied for n equal to 1.
Because n equal 1, it depends on
No,
the...
no, you mean L. You mean...
yes, L, sorry.
Yeah, no, 2, yes, at least L must be equal to 2. One hidden node and one hidden layer. One output layer.
Okay.
Okay, let's have a small break.
And also in B it has 1 column.
Yeah, B has 1 column. It's here.
Yes.
Oh, and here.
Yes. Why?
This is because here you have 1 training example. Okay, so you have an output for every unit for the training example. Okay, and here you have so B, you have 1 B here, 1 B here, 1 B here, so it's a column.
Okay.
Yeah, and this is because here you have 1 training example, so every training example will result on a value A. Okay, and this is why. Okay, so if we go to the next slide, this is the case for 1 training example. For the forward propagation, you have NL minus 1 and LN1. And for DW and DB, okay, it has the same dimension as W and B, because at the end you are going to make a W. The new WL is equal to the old WL minus alpha DWL. So of course, naturally, they must have the same shape. Okay, and same thing for BL and DBL. They must have also the same shape. Okay, so these are the shapes of the weight and the bias for the forward propagation, and also for the backward propagation, the shapes. Now, in case of M training example, what is the difference? Of course, W and B will not change at all, because as we have mentioned several times, that they are independent of the number of training examples. But A and Z will be, okay, so instead of having NL1, you will have NLM, where you are going to have one column for every training example. Is this clear? Yeah, basically it's the same shapes that we have even seen in the previous lecture. It's just a generalization, and this shows the shapes for all the hidden layers and the output layer, okay, regardless of how many hidden layers we have here. But if you go to the previous slides, if you want to compare this slide with the previous lecture, you will find that it's almost the same thing. Okay, so why we care about the shapes and we talk about the shapes? So when you do the implementation in the assignment later, in the Python assignment, okay, you have to make sure that the shapes are correct. And I think when you did the assignment, for sure you have encountered some computation problems because of not putting the shape properly. This is why this is why sometimes you need to do transpose, or you need to reshape using -1 or something like this. So all this kind of reshaping and transpositions and stuff like this is to make sure that the shapes are correct. So
it's a good way to debug.
Exactly. Yes.
False shapes.
Yes, and fortunately for us now, we don't have to implement deep learning from scratch or deep neural network from scratch, because we have a very good framework like TensorFlow, PyTorch, and others. But it's really important when you go for the deep learning research and development area, it's good to know how these things are really implemented. Okay, maybe you know this only one time and you do it only one time, but later on when you work, you will be much more comfortable to work with any kind of architecture, because you understand the internal mechanics of the deep neural network. And this is the objective of our lectures, is to understand these internal mechanics. But in reality, in real world, you don't have to do all of this. But of course, dealing with the shape is very important, especially when you program in Python and you use the NumPy array, okay, which is a very powerful data structure. It's always good to check whenever you have any issue in the computation, check the dimension of the matrix and whether this is the expected output or not the expected output, and so on. And the assignments that you do in Python are very good exercise to help you getting these skills on how to debug the implementation in neural network. Yeah, so that's pretty much it for this lecture, deeper neural network. Now you have a complete understanding about neural network and what is happening inside, and how to do forward propagation and how to make backward propagation. So let's say all the functional things related to neural network, now you know them. But of course, this is not the only thing. Now in neural network, there are a lot of hyperparameters. And the hyperparameters will affect a lot the training performance, will affect how the weights will be, the final weights that will be learned. Okay, so in the next lectures, you are going to learn new techniques, or the techniques that are used now, in order to optimize the performance of the training of a neural network, which is very important. Okay, so
Doctor?
Yes.